Well, hello and welcome to the VMOD webinar. I think we'll get started. My name is Wayne Hesh. I'm the product champion for VMOD here at Schlumberger in Waterloo, Ontario, Canada. The overview today is to go through some of the developments we've done at VMOD in 2012 and look ahead at some of the changes we're planning on making for 2013. I have the microphones muted for the attendees, so if you have any questions, you can use the chat feature, which is available from the Webex toolbar at the top of your screen. If possible, leave your questions or comments till the end. I've allocated a few minutes for time for that. If I'm unable to answer your question, just feel free to email me. My email address is shown on screen there. And we'll also make a recording available of this webinar for download from our website in the next few days. So you can look for the link on our blog. So the outline for the webinar today is around, should be able to finish in about 45 minutes. Go through the conceptual modeling approach in VMOD and how this allows you to overcome some of the challenges of classical numerical modeling. A quick recap of our implementation of PEST parameter estimation with pilot points. And then look ahead at some things that we're currently working on and planning on releasing throughout the year. The first is MT3DMS, then MODFLOW-USG, and finally, parameter estimation in the cloud. So first, let's look at some of the challenges in numerical modeling. These are things that you've likely encountered if you've been working with the classic visual MODFLOW or other MODFLOW pre- and post-processors. As you're well aware, modeling is iterative. It's something you rarely get right the first time unless it's a very simple model. So you typically assign your input data to a specific grid or a mesh. As you adjust the grid or mesh to handle different changing objectives, you need to reload most or all the data, and this can be very inefficient. Numerical models typically involve several scenarios where you're adjusting different parameters for calibration, looking at different options, and it's necessary to manage and compare multiple models. This can be quite difficult. Modelers need to understand the groundwater system before running a predictive model. The data that you get for a groundwater model also often comes from various sources, formats. It's done with a number of different tools, including GIS, Surfer, EVS, Excel, databases, etc. Each one of these can require their own learning curve, but really only provide a limited piece of conceptual modeling. Lastly, they're not well integrated with the numerical modeling package. In addition, models evolve as your objectives change, and you've probably seen this working with models where your client may come to you and say, we need to extend the model region or include further processes such as transport, surface water, groundwater interactions, etc. So it's necessary to update the conceptualization as more data are collected or as you get a better understanding of the subsurface. The solution to overcoming these challenges is to have a conceptual model. The conceptual model allows you to define the geological structure, the properties, and the boundary conditions using shapes and attributes. The conceptual model is grid and simulator independent, which means you can convert it to either MODFLOW or FEFLOW. And since it's not assigned to any specific numerical grid, you can realize this conceptual model with a variety of different grid sizes, resolutions, local grid refinement, etc. So I'll go through in the next couple slides a few examples of the challenges of numerical modeling and how these are alleviated with the conceptual modeling approach. First are boundary conditions. If you start with the example shown on the left here, where you start with a coarse numerical grid and you assign some your boundary conditions to this grid, either constant heads or river cells that are shown in blue at the bottom of the screen. Throughout the course of model development, you may need to refine the grid, and you can see that after refining the grid, you have your modified river cells shown at the bottom of the screen, and you can see through the course of grid refinement that cell that was previously coarse now occupies 3 finer MODFLOW grid cells, which is most likely not the desired approach. And if you face this before, you know there's really no easy way to correct this. So what is most often done is you need to delete the boundary conditions in the numerical model and re-import or reassign these. This can be quite time-consuming and frustrating. Same is true if you start with a MODFLOW grid which is too fine and you need to coarsen it. So again, your river cells are assigned to the fine MODFLOW grid, After coarsening the grid, you have the modified river cells shown on the screen on the right. And often, since the cell center for the original grid cell is no longer in the right location, you may have the river boundary that is incomplete or disjointed. And again, there's no easy way to fix this. You need to delete the boundary conditions that are there and re-import or re-digitize by drawing. And this is a very simple example, but if you can imagine a very larger scale model where you have tens, if not hundreds of river boundary reaches, this can be quite time-consuming. So the preferred approach is to follow conceptual modeling workflow. In this case, the boundary conditions are represented as shapes consisting of points, polygons, or polylines. So these can be wells, polylines for rivers, streams, content heads, or polygons for recharge zones, lakes, general heads, etc. These shapes have corresponding attributes that are relevant to the boundary conditions. So specified heads, stage, conductances, flux, etc. The conceptual boundary conditions are not assigned to the grid cells, which means you can make any changes to your MODFLOW grid and regenerate the cell inputs. So this approach is very quick, efficient, and allows you to evaluate several model scenarios instead of just a single numerical representation. This allows you to efficiently improve the model stability, manage convergence, and reduce your model runtimes. The workflow in going from the conceptual model objects to the numerical representations is illustrated in the next couple slides. So after your conceptual model is defined, you create and overlay a MODFLOW grid with the desired resolution, and you run an automated conversion routine that generates the cell representations for your boundary conditions. So you can see on the right, you have the red cells at the top are the constant head cells generated from the polyline you defined in the conceptual model. And in the bottom of the screen, you have the light blue cells representing the river cells that were generated from the conceptual objects. Extending this to a further different grid resolutions, you can see that with very minimal effort, you can generate several numerical models from your conceptual objects. So on the top right, you have a coarse grid with the boundary conditions. In the lower right, you have a slightly larger grid size. And in the lower left, you have a more refined grid that has the appropriate boundary conditions assigned in the appropriate cells. Zooming in on that view in the bottom left, you can see that those river cells only intersect the fine numerical grid cells that were overlapped by the conceptual object. So again, you don't need to adjust the boundary conditions, rework things after the grid is coarsened. It just can be quickly regenerated by running that conversion routine. The same is true for working with property zones. Again, if you assign your original property zones to a coarse grid in the numerical model and you refine the grid, you'll see that the modified property zones no longer honor the original shapefile geometry. Zooming in on a specific location, you can see that this turquoise, green, and blue property zone has property zone values that are no longer following that shapefile geometry. Again, there's no easy way to correct these. You need to most often delete the property zones that are there and re-import from the appropriate file to the new grid resolution. The same is true when going the other way. If you start by assigning property zones to a very fine grid and you find out that your model is taking too long to run or you need to coarsen the grid in certain areas, those property zones that you previously defined are usually no longer relevant. You need to delete them and re-import them. Instead, by following a conceptual modeling approach for property zones, you can get over these headaches and troublesome practices. Similar to the boundary conditions, the property zones in the conceptual model are represented as shapes or 3D volumes with the attributes. So those could be your connectivity in the XYZ direction, initial heads, specific storage, etc. The property zones can be defined using various data sources such as shapefile attributes or raster grid. The property zones aren't assigned to the grid cells in the conceptual model, so this allows you to make any changes to the grid and regenerate the cell inputs. This allows you to have improved accuracy and better representation for your numerical models. Again, the approach is quick and efficient, allows you to evaluate several model scenarios, so you can start by running a quick coarse grid representation for your site to see if and where you need to add more resolution without going to the effort of re-importing a lot of the original data. This allows you to improve the model stability, accuracy, and gives you the flexibility to evaluate multiple numerical discretizations, which I'll show in the next slide. The images shown on the screen here in the top right would be a set of property zones coming from some shapefiles, where each shapefile feature has a different attribute defining connectivity. And the image in the lower right has a constant value defined for each property zone, so different aquifers and aquithards, etc. So a quick illustration of different grid realizations for your property zones in your models. Again, going from the conceptual property zones in the shapefile to a very coarse grid of 60 rows by 60 columns, you can see the corresponding property representation. You can create a more refined grid that has roughly 140 by 140 rows and columns, run the conversion, and create the numerical model inputs. And lastly, you can create a more refined grid that has 300 rows by 300 columns. And you can see in this case, the property zone geometry more closely matches the original shapefiles. Again, this is only necessary if your model needs to have this much resolution, but with the flexibility of the conceptual modeling approach, you can either add or reduce the amount of resolution or accuracy as needed. And this is where local grid refinement comes in to be very appropriate. You can refine the grid in a specific area of interest, have very fine, high-resolution grid cells in your specific area, but coarser grids, cell size outside the area of interest. And again, this local grid refinement input can be generated from the conceptual model very quickly and efficiently. So Visual MODFLOW Flex is the only environment that allows you to compare a variety of numerical models with different grid sizes, grid resolutions, and this includes input files for local grid refinement or MODFLOW LGR. And lastly, when working with discontinuous property zones, the conceptual modeling has the added approach that you don't need to worry about working on a cell-based level. So when assigning these in numerical modeling, you have to assign the properties in the layers that pinch out manually using an isopoc map or other type of 2D or 3D objects. With conceptual modeling, the properties are assigned to 3D volumes, and they don't need to be continuous across the entire model domain. This is handled during the conversion, so when you create a MODFLOW grid, you specify a minimum layer thickness, and for the layers that pinch out, the properties for those pinch out regions are automatically assigned from the appropriate layers above or below, depending on the horizon rules or the hierarchy you assign for the different geological formations. And an illustration of this is shown in the bottom of the screen there, where you have your conceptual model in the bottom left. After you overlay a MODFLOW grid or a finite element mesh, you specify a minimum layer thickness, and during the conversion you can see that in those pinch-out regions, the property zone values are automatically accommodated from the zone above or below. So the discontinuous formation actually stops where you specify it should stop in the conceptual model. And this illustration here shows the ability to correlate the various numerical models to your conceptual model. So in the top left, you have your conceptual formations. From this, you can generate the uniform layering approach, where each vertical layer has a uniform thickness. The more commonly used grid is a deformed grid, shown in the bottom right, where the grid layers follow the geological formations. And lastly, you can also generate unstructured grids and create the inputs for the unstructured grid files. These could be inputs for PFlow or for the new MODFLOW-USG version that is coming. So to recap some of the benefits of Visual MODFLOW Flex, the integrated conceptual and numerical modeling environment gives you the flexibility to choose the right simulator and the right grid. You don't have to choose if you want to run MODFLOW or PFlow at the beginning of the project. You can postpone this until later on in the model development. It allows for more efficient updates to the model midstream or midway through the project, and makes it much easier to design and update multiple models with very little effort. You can design and simulate multiple finite difference grids, which have different vertical and horizontal grid resolutions and grid types. As I mentioned, these could be uniform grids, deformed layers, variably spaced grids, local grid refinement, etc. And when you're dealing with complex geology or discontinuous layers, this can be accommodated in a matter of minutes by following a conceptual approach. And lastly, you can manage multiple model scenarios, change different input parameters, compare steady state to transient runs, make comparisons between the outputs for the different files so you can calculate differences between heads and drawdowns from different runs. And this allows you to streamline the uncertainty analysis. So towards the end of 2012, we added support for parameter estimation with pilot point parameterization, and in the next couple slides we'll discuss that. The highlights of our implementation of PEST in Visual MODFLOW Flex are mentioned on the slide here. The first is that we offer a workflow approach for navigating through the steps in building the PEST files, running the PEST simulation, and analyzing the results. So this offers a very intuitive and logical navigation, allows you to reduce the learning curve in learning the PEST interface and spend more time on understanding how the PEST parameters work. Within Visual MODFLOW Flex, you can distinguish between different pilot points, whether you have soft or fixed pilot points, and that's illustrated in the next slide. We have support for regularization techniques, including ticking off and SVD assist. After PEST has been after PEST's run is complete, you can save the PEST results as new model runs as inputs for a new numerical model. This allows you to compare the PEST adjusted parameters and the corresponding results to your original numerical model assumptions. You have quick access to the PEST results, the PEST record file, parameters, sensitivities, residuals, etc. And the PEST results can be exported to Excel, where you can do further statistical analysis or charting. Within Visual MODFLOW Flex, you can distinguish between fixed pilot points, which be those points where you're confident with the measured value for your parameter, in this case conductivity. So for example, if you've done slug tests or pumping tests and you want PEST to honor those parameter values, you would flag those as, enter those values and then flag them as fixed pilot points. In contrast, the soft pilot points would be those points that you strategically placed at the desired resolution in the property zones that you want to adjust. So for PEST to be effective, you need to have and use a lot of pilot points. However, by adding more pilot points, which PEST considers these to be parameters, this comes at several costs. The first is that you can run into non-unique solutions. This leads to numerical instability, longer run times. Remember that MODFLOW needs to be run for each pilot point parameter and for a number of PEST iterations in order to optimize the objective function. And this may break a golden rule of PEST, which is that in general you should have more observations than for which you have a number of parameters. The solution to these problems is that PEST uses a regularization technique, and as I mentioned, there are two types, ticking off and SVD assist. I won't go into too many details of ticking off or SVD assist regularization. There is a link on our website to the PEST webinar we did at the end in December of last year if you're interested in more details how this works and what options are available in the interface. But in general, with regularization, it allows you to reduce the run times for PEST. It allows you to use more pilot points, which means your property zones or your model in general can have hundreds or thousands of pilot points. You select a subset of parameters, which are called super parameters, and that's typically much less than the total number of pilot points. And this results in a better fit between the model outcomes and the field observations. By following regularization techniques, this results in PEST values that more closely match your original model input parameters or your original assumptions. In general, PEST will only adjust the parameter heterogeneity as needed. So the estimated parameters for a specific zone will be as uniform as possible, and PEST will only introduce heterogeneity because it's necessary. As I mentioned, after the PEST run is complete, you can review the PEST results directly in our workflow. So you can see previews of the PEST record file, the sensitivities, the residuals, and the other changes in objective function, etc. Those results can be compiled into Excel worksheets and exported to external files, where you can then do your additional charting, things like your calculated versus observes, observed values, plot the parameter sensitivities, the residuals, etc. Or you can just create your own charts. We offered this option because everyone has Excel on their desktop or their laptop computer, and just gives you much more flexibility to adjust the Excel chart settings and customize them to the way you want based on your experience with Excel. After the PEST run is complete, you can also save the PEST parameters as inputs for a new numerical model. So typically you want to run your model using the adjusted PEST parameters to see what the change will be to the heads, the drawdown, or also look at the change in the calibration. So within Visual MODFLOW Flex, you can save this as a new model run within the same project, and this allows you to compare the results and the property distributions between different model scenarios, calculate the differences between heads, etc. This also makes it much more efficient and simpler to evaluate several PEST scenarios. So for example, comparing a PEST run with regularization, or a PEST run with SVD assist, or no regularization, etc. So within a single Visual MODFLOW Flex project, you can have a family of PEST scenarios that can be stored, accessed. You compare the different results in each of the scenarios. So that's a recap of the changes that we implemented in 2012 with Visual MODFLOW Flex. The next, or I guess the remaining slides for the webinar today will go over some of the things that we're currently working on and the planned releases for 2013. The first is support for MT3DMS. So MT3DMS offers multi-species contaminant transport. With the implementation in Visual MODFLOW Flex, we have the following features and benefits. So we have the ability to generate several grid representations for your transport models. Following the conceptual approach, you can define the transport inputs and then realize this with a variety of grid discretization. So for example, a coarse grid, more refined grid, and compare the results from each of the different scenarios. If you've done transport models in the past, you'll know that numerical dispersion can become an issue, so it's important to change the vertical discretization, run the simulation in order to find an optimal balance between the accuracy and minimizing the run times. And this is all possible by following a conceptual approach and having and comparing multiple transport simulations in your project. After the model runs are complete, you can compare the concentration results between different runs. This is useful if you want to compare different remediation scenarios, or comparing pumping rates, or optimizing well location and retrieving to see which scenarios have the most suitable plume capture and treatment. With the 64-bit version of VMOD Flex, we'll offer the 64-bit versions of the MT3DMS engine, which will allow you to run transport models with more refined or larger MODFLOW grids that can contain up to millions of cells. And this is something that's not possible with the previous version of Visual MODFLOW. You would run out of memory if you try to run a transport model that had, let's say, anywhere from 1 to 5 million cells. So the 64-bit version allows you to leverage the higher amount of memory that you have on a 64-bit machine. By comparing the simulated results, you can correlate and do reliable QA/QC by comparing plume locations, color maps to your original boreholes, your monitoring locations, or even your geological formations. So for example, looking at how plume transports through different property zones in the conceptual model. And overall, the graphical environment of VMOD Flex provides effective visualization of the contaminant concentrations in different layer, row, cross-section views, also 3D views, and the 3D views can be exported to animation files for using in a presentation. So that's a quick look at our plans for MT3DMS. The release of Visual MODFLOW Flex with MT3DMS should be available hopefully in May this year, and we should be having a beta version within the next month or so. If you're interested in evaluating this, feel free to email me or our sales team. The remaining slides will take a look at MODFLOW-USG and some other work we're doing with PEST in the cloud. So MODFLOW-USG is the new version of MODFLOW being developed by the USGS. USG stands for UnStructured Grids. Some of the motivators or driving forces behind developing MODFLOW-USG are shown on the screen here. The first are to build on the strengths of MODFLOW, which is that it's an open source code, it's well established and documented, it's reputable, it's used by private and public sectors and also for research and academic purposes all around the world. The finite difference formulations are relatively easy to understand. It is mass conservative and has a number of packages and extensions that have been developed throughout the years. You're probably familiar with many of the MODFLOW packages that have been developed, and also the add-on simulators such as PEST, MT3D, RT3D, Zone Budget, ModPath, etc. However, since the very first version of MODFLOW was released in the mid-'80s, it's had these long-standing limitations, which is very inefficient grid refinement. So if you do your grid refinement, it'll extend the rows and columns all the way throughout the model domain. And this includes a lack of ability to refine around wells, boundaries, etc. And it's not really ideal when you need to get into more complex geology. You can quite often result in disconnected cells, which leads to convergence and stability issues. So the motivator for MODFLOW-USG was to provide a viable alternative to finite element models, which offer a lot of this flexibility that has encouraged many users to use finite element models instead of MODFLOW. And the end result was that it was determined a finite volume approach for MODFLOW-USG will provide this flexibility. As I mentioned, MODFLOW-USG stands for UnStructured Grids. An unstructured grid is essentially any type of grid geometry that can be used for discretizing the model domain. So this can be triangulars, rectangular, polygonal shaped geometries, and just keep in mind that the traditional version of MODFLOW uses structured or rectilinear grids. An unstructured grid paradigm further allows you to have 1D, 2D, or 3D line elements that allow you to simulate interflow processes such as discrete fracture networks within the groundwater flow model. The benefits of a finite volume approach is that it offers a higher level of gridding flexibility than finite difference formulations, but overall it's just as easy to understand and implement within the MODFLOW framework. Finite volume essentially offers even more grid geometry flexibility than a finite element approach, since you can use any type of grid geometry. You can combine various grid geometries within a single model. Finite volume offers mass conservative, robust, and efficient solutions. And as I mentioned, you can combine various grid cell geometries into a model without doing additional coding. So a quick overview of those different simulators and some corresponding illustrations. Most of you are familiar with MODFLOW, which is a finite difference formulation shown on the left, where you're dealing with structured rectilinear grids. Finite element models such as FEFLOW, Sutra, and others are working strictly with triangular meshes, and the example is shown on the bottom of the screen in the middle. And the new version, MODFLOW-USG, is a finite volume approach, which allows you to use unstructured grids that can have any type of grid geometry. Some examples shown there would be rectangular grids that have nested or quad tree grid refinement, where you have gradually smaller rectangular grid cell size around features of interest such as wells, polygonal grid shown in the middle, and then lastly a triangular grid. So some of the benefits of MODFLOW-USG is that you can locally refine the grid around your areas of interest, including wells, flow boundaries, or geological features, or have nested grids around an area of contaminant transport. Each layer can have a different nesting structure, so the refinement that you specify does not need to span through all layers of the model domain. So some example, you can control the refinement to specific layers around well screens, or refine around your surface water body features in the uppermost layers, and then gradually coarsen the grid as you work your way down. The overall benefit is that you can have a greater amount of detail and higher accuracy around the area of interest without sacrificing the model runtimes or the model stability. MODFLOW-USG also allows you to have these vertically nested grids or sublayering within the grid geometry. This is ideal if you want to model isolated lenses or pockets of materials or a discontinuous formation within a larger unit. These layers do not need to extend across the entire model domain, so some examples of what these sublayering grid cells would look like are shown in the bottom of the screen. This allows you, again, to represent the more complex geological formations without sacrificing the model runtimes and the model stability. So in the past, if you had these discontinuous purged aquifers, you'd have to add a whole additional model layer to the numerical grid and have that model layer extend across the entire domain. With MODFLOW-USG, that restriction is no longer required. A few other slides discussing what else is in MODFLOW-USG. The first is the Connected Linear Network Package, or CLN. This is similar to a combination of, if you're familiar with the MODFLOW CFP, or Conduit Flow Package, this will supersede that package, and it's also a combination of the capabilities with the MNW, or Multi-Node Well Package. The CLN package allows you to simulate features such as fractures, wells, conduits, or channels within the 3D groundwater flow domain. The CLN package has its own discretization, which is essentially 3D polylines throughout the model domain connected by vertices and defined by digitizing or importing from files. The CLN package supports a single or network of conduits, and these conduits can be at any angle. They don't need to be horizontal or vertical. Some of the examples are shown on the screen on the right side. MODFLOW-USG also includes a ghost node correction, or GNC package, and this is used for correcting polygon grid geometries where where adjoining cells do not have a bisecting line that intersect at the 90-degree angle, essentially. Some illustrations showing this are at the bottom of the screen. So if you have these nested grids where the center of a coarse parent grid is adjacent to these smaller refined grids, you can see that the center of those grids will not intersect at a 90-degree angle. So instead, MODFLOW-USG can insert a ghost node at that location so that it'll honor the finite volume formulations. The same is true for the intersection between a polygonal grid cell size here and a rectangular grid. You can see that the center of these grids do not match at a 90-degree angle. So instead, a ghost node can be inserted in the larger coarse grid such that ghost node will intersect the adjacent smaller grid at a 90-degree angle. There's a full paper on the ghost node correction package. If you're interested, just please let me know and I can send that to you. The GNC module is also used for conduits, or the CLN package, that are off-center from the porous matrix grid block. So how it works, in general, MODFLOW-USG follows the conventions of the previous versions of MODFLOW. You have the same type of packages. The key differences are due to the different grid structures. So you have a new DIS-U package, which contains the grid geometry for an unstructured grid, including the connections, the cell faces, the cell size, etc. The boundary condition cells are tracked using a node number instead of a layer, row, column. So if you open, for example, a river package or a constant head package or well, you'll see a node number in there instead of a layer, row, column. And MODFLOW-USG works with two solvers, the current version. The first is a PCGU solver developed by Joe Hughes, and the second is the ChIMD solver, which is similar to the one that's used in MODFLOW-NWT. So MODFLOW-USG will support the following traditional MODFLOW packages for the first release. All the property packages with the exception of the HUF package, constant head, river, recharge and evapotranspiration, flow and head boundary, well, drains, general heads, streams, stream flow routing, stream gauge package, lakes, and the horizontal flow barrier. However, there are a few limitations for the first release, and these are things that are still being developed. Zone budget is currently not available. Particle tracking is still being developed. A contaminant transport module is also being developed by Saurabh Pandey. And there's also no support for unsaturated zone flow. Both the UZF or the VSF packages currently are not supported. I should mention that MODFLOW-USG is still being developed. I think it's in the final testing phase by the USGS, and not sure the release date at this time, but I'm hoping it'll be in the next couple months. So MODFLOW-USG and the grid generation fits in nicely with the conceptual modeling approach that we have in Visual MODFLOW. Having a well-designed grid is fundamental for leveraging all the MODFLOW-USG capabilities that you've seen, whether it's nested grids or refined grid geometry around features or even sublayering. The model features, again, wells or boundaries, which can take on various shapes such as points, polylines, or polygons, should be used as inputs to the unstructured grid design. And this is in contrast to traditional MODFLOW, as I mentioned in the very beginning of the webinar, where you start by designing a grid and then you refine the grid around the areas of interest, and you go through various iterations of grid refinement and coarsening in order to find the suitable set of model inputs. For those of you that are familiar with finite flow modeling, this approach that we plan on taking in MODFLOW-USG is very similar to what you do with flow. So in a flow model, you start by adding in shapes for defining the super-element mesh. These could be your points, lines, and polygons. Then you generate the finite element mesh around these objects. So you specify how much refinement you want to have occur around these objects, the gradational refinement, whether it's smooth or sharp, and you also specify roughly how many elements you want it to have. In order to do this, this requires the model features to be grid independent. Again, this is where the benefits of having a conceptual model can become quite important. This slide shows a few examples of some of the unstructured grids that we currently can generate with Visual MODFLOW Flex. In the top left, you have a triangular grid with a grid refinement around a meandering river. And the other examples show a polygonal grid, which is the central Voronoi tessellation of a triangular grid. Again, these are polygonal grid shapes that are refined around streams, channels, wells, etc. So the last thing I'll discuss in the webinar today is some other work that we're currently doing, which may be available for release towards the end of 2013 or even 2014. And that is running parameter estimation, or PEST, in the cloud. So for those of you that aren't familiar with PEST, the way it works essentially is PEST will run MODFLOW once for each parameter in your model, adjust the different values at those pilot point parameters, and repeat this for each PEST iteration. Depending on how long your MODFLOW run takes and how many pilot point parameters you have and how many PEST iterations you have, this can be quite lengthy. Each PEST parameter essentially can be adjusted independently on a separate process or machine. Thus, the power of parallel computing becomes very beneficial here, and this is where things like parallel PEST have become very beneficial for leveraging PEST runs. A new version of PEST, parallel PEST, called BioPEST is what we use for running PEST in the cloud. So our temporary name for this work is called StarPEST, and essentially allows you to take a PEST model you define in Visual MODFLOW Flex and run BioPEST using the cloud power that's available. We use an image setup on Amazon Web Services. The StarPEST can be launched seamlessly from the Visual MODFLOW Flex workflow. So you, as I mentioned, follow through the PEST workflow that I showed previously, and instead of running PEST on your single desktop machine or your laptop, you can launch this for a PEST run in the cloud. So there's no scripts they need to adjust. You don't need to have any experience with Python or manually adding the input files. We've made it very seamless and easy to launch a PEST run in the cloud very quickly. You also need to worry about configuring different clusters of machines or the communication between those machines. This is all taken care of with StarPEST and BioPEST. And the result is that you have very fast, convenient, and efficient PEST runs using cloud powerful resources. So how does it work? As I mentioned, a single run of PEST without the parallel capabilities. You run MODFLOW over and over again for each of the parameters. And again, this is very time-consuming. Instead, by using resources available in the cloud with Amazon Web Services and BioPEST, a number of model runs can be run in parallel. This could be 8, 16, 32 different nodes on Amazon Web Service, each one running a separate version of MODFLOW with a different parameter. Workflow is to select start PEST from the PEST workflow in Visual MODFLOW Flex. You select how many nodes you want to run on the Amazon Cloud Service. This could be, as I mentioned, 8, 16, 32, 64. It'll give you a rough cost estimate for how much this is. You then start the PEST run, and start PEST will automatically transfer your model files from your desktop into the cloud, run DOPEST, give you some feedback on how the run is progressing, and once it's done, it'll compile the results and pass this back down to your desktop where you can resume the analysis of the PEST results that I showed previously. So looking at the ASCII output from PEST, the sensitivities, the residuals, etc., and then do further analysis with exporting results to Excel. So we've completed some initial tests with start PEST, and the results are very encouraging from what we've seen. For a simple model that takes roughly 2 hours and 10 minutes to run on a pretty powerful quad-core desktop. By running that in start PEST using the cloud service, it takes approximately 20 minutes using a 32-node cluster environment. I should comment that I believe this, the usage rates or the cost for this type of run in the Amazon web was very cheap. I believe it was $5 or $10 at the most. You can see on the chart shown on the screen what the actual runtime is when comparing the desktop environment to the cluster environment we're using start PEST. So if you're currently doing a lot of work with PEST or even just are interested in evaluating this, we're currently looking for clients that have different models they want to try and run in the cloud. Just please contact me or our sales representatives, and we can work together to prototype this and evaluate it with different model scenarios. For more information on MODFLOW-USG, you can see the blog post that we did in August 2012. This is available on our website. You just go to the blogs heading and then search August 2012, where it'll provide a more detailed write-up on some of those MODFLOW-USG assumptions, how the grid geometry work, how the different packages work, etc. We will showcase a preview of MODFLOW-USG at the MODFLOW conference this year, which is in Golden, Colorado in June. And we'll also be having a short course on MODFLOW-USG on June 2nd. If you're interested, just click on the link there, or feel free to email me. I can pass you the details if you wish to register for this course. I'd like to thank Saurabh Pandey, who's the co-author of MODFLOW-USG, for providing me the content for the MODFLOW-USG slides and also the white paper, and also providing some examples of the different grid geometries. So this concludes the webinar. For more details, feel free to visit our website. You can also download a 30-day trial version of Visual MODFLOW Flex from there. And if you have any questions at any time, you can email our sales representatives, or feel free to email me at whesh@slb.com, and I'll be more than happy to answer the questions for you. So this time, I'll open up the phone lines if you have any questions or comments, or feel free to use the chat feature if you want to send me a question through that instead.